Good afternoon, everyone. A big thank you to CLF for this opportunity and support from HKS here out of their Seattle office. This case study is part of my academic work at Carnegie Mellon University for the course Environmental Life Cycle Assessment. I'd like to acknowledge all my team members for the collaborative work and my advisor, Dr. Wen DePutro, for her guidance. In the US, air conditioners and furnaces are predominantly used in residential cooling and heating, while significantly consuming energy. In 2015 alone, space heating and cooling accounted for about 30.7% of the US residential sector electricity consumption. So the primary goal of this study is to evaluate pathways in transitioning to heat pump systems from conventional one-way heating and cooling air conditioners and gas heaters separately through a life cycle analysis comparison. Well, mind the sketch, but this is exactly how most US homes are designed for their heating and cooling systems. Based on a study published by a non-profit organization, CLASP, there have been calls for the adoption of policies and incentives for US homes to transition from conventional cooling and heating systems to hybrid 3H, a super efficient technology that can both heat and cool indoor spaces. Now, there are also monetary incentives for consumers to switch to heat pumps. Following the Inflation Reduction Act passed in August 2022, households can access a tax credit to cover up to 30% of the costs for qualifying heat pumps, capped at about $2,000 for upgrades installed in 2023. So as a team, we wondered, how can this change impact the environmental life cycle of these products and their use? So here we have our business as usual and case one for evaluation. Additionally, we explored low carbon electricity sources as alternate renewable pathways, giving us two more cases for comparison, case two and case three. Following our goal statement, the results will support or refute the benefits of adopting heat pumps using the study design cases, keeping in mind the changing grid and renewable options available. After a lot of consideration, the functional unit chosen for the study is simply heating and cooling of one house to a set point temperature of 72 degrees Fahrenheit for heating and 75 degrees Fahrenheit for cooling to provide thermal conditioning for about 20 years. Now, the system boundary starts with manufacturing phase, followed by transportation, operation, and end-of-life phase, with a defined time frame for heating and cooling of 20 years, as we discussed. The installation phase is excluded from the study with the assumption that existing ductwork and indoor units will be continuously utilized. However, equipment replacements, where required, is included in the study. To demonstrate the possible inputs and outputs of the business as usual case and alternative pathways, the entire life cycle from manufacturing to end of life stage was considered in the system boundaries of this study. 4 distinct stages were identified and applied equally across the different pathways: raw materials, production stage, end of life stage, and material use stage. The initial stage of the process flow includes the processing of raw materials and the production of components such as steel and aluminum, which are used in the assembly of equipments. We chose a Department of Energy prototype home to define average design parameters of a house located in Pittsburgh, Pennsylvania, and sized our equipment to get heating and cooling load with set efficiencies, giving us the site energy used by the equipment and corresponding source energies. Further steps of our methodology are also listed here, giving us the model specification, calculation, and our eventual analysis of our study. For each material production process, the primary inputs and outputs and emissions are documented using the tool OpenLCA. Primary databases used are as listed here, mainly USLCI, US EEIO Tracy, and Electricity LCI. External databases or LCA studies are also utilized where required and where data is not available. Besides the consideration of energy, refrigerants are also an important reason for switching to heat pumps. Traditional cooling systems typically use HCFCs as refrigerants, which have significant ozone depleting and global warming potentials. While HCFCs are being phased out into cleaner HFCs, which has lower global warming potential and zero ozone depleting potential, most AC units currently still utilize R22, providing more reason to switch to heat pumps. Here's a quick summary of materials, sources, and assumptions on distances traveled below. Jumping into results, the largest contribution to carbon emissions is actually from case one, heat pumps. Not too far is the business as usual case using air conditioners and gas furnace. And then we have the case two. However, the case where the heat pump is powered by renewable energy had the least emissions, a reason why heat pumps are gaining popularity. Zooming into other impact categories, high levels of methane emissions can be seen with the heat pump case one. Now, don't be surprised. This case study is based in Pittsburgh, which still largely relies on natural gas. The moment this is shifted to renewable energy, heat pumps perform much better, as seen in case three results. While the impact of refrigerants is much lower, they can have really high ozone depleting potential. Looking at just the refrigerants and their emissions in kilograms by phase, the air conditioner was found to release more refrigerant over its life cycle than the heat pump. Also, let's not lose sight of the zero ozone depleting potential of R32 here, which gives case 3 and case 1 more benefit. Here's a table of the emissions broken down by the various phases over all the scenarios for the global warming potential and ozone depleting potential values. But we like graphs, so once again, putting these impacts over a graph by phases, you can see more operational carbon emissions as compared to embodied carbon over a period of 20 years. However, if we just look at the manufacturing phase of these equipment, business as usual case and case 2, which both use air conditioners and gas heating, have a higher upfront embodied carbon, which is very relevant considering case 3 with renewable energy option, where the embodied carbon from manufacturing phase almost is half the operational carbon for 20 years. Now here's a life cycle impact assessment for ozone depleting potential and global warming potential. I know this is a lot of data, but what you can notice here is it clearly shows the impact of refrigerants with ozone depleting potential to be significant in the manufacturing phase of the cases where applicable. So you can actually divide the impacts by phases on the overall total that they have.
It is.
So here's an overview of the sensitivity analysis that we did on our results. In our results, we noticed that the use phase of the air source heat pump remains the primary reason for the large global warming potential. Understanding that the efficiency of heat pumps in the market has been improving over the years when compared to natural gas furnaces, the current load for the heat pump with respect to its efficiency could be reduced by 20% in the near future. Considering 5 years into the 20-year time frame of our study, in the point 2 case, the refrigerant assumptions within the equipments are not consistent. We predict that new two-way heat pumps would utilize refrigerant R32 with a lower global warming potential than R410A, which is currently in use in many air conditioners in the market. And lastly, we needed to test time sensitivity or the duration of the use of our equipments. So what did we learn from these sensitivities? The efficiency of the equipment can greatly reduce the global warming potential of case 1 with heat pumps and make it a better pathway over business as usual or case 2. If we doubled and tripled the refrigerant capacity from the initial considered values, the impact of the increase is very minimal for the air source heat pump, but more significant for the air conditioner cases. Not to mention, such high values are rarely noticed in the market in terms of the capacity. Moreover, the overall impact of the LCA of refrigerant capacity is very small. And doing a sensitivity for the type of refrigerants does not impact the results as much, as you can see here for the different cases. Doing a sensitivity for the duration of use, we notice that although the initial phase of an air source heat pump may fare better, within 2 years, the gap in performance drops due to the use phase contribution. So as a high level, in terms of interpretations that we learned, global warming potential of using an air source heat pump for both heating and cooling for 20 years in Pittsburgh is much higher than separately using an air conditioner for cooling and a conventional gas furnace for heating for the same time period. Oil continues to heat a significant share of homes in the Northeast, with the largest totals in New York, Pennsylvania, and Massachusetts. So, how would these uncertainties further change our result? I'd like to conclude by saying the holistic assumptions for the country are not necessarily representative of individual homes. The electric grid is getting cleaner, driven by improving clean technology as well as federal and state goals. The grid will largely shift to clean energy during the lifetime of heating and cooling of appliances installed today. So make a wise choice. Thank you.